Okay, so Zion, you can now start with your report.
Thank you, sir. Good morning, my fellow graduate students. For today, I will be discussing to you the constants and arithmetics or instructions of assembly language. So our agenda is to define or understand what is a constant, the what are the integer constants, character, and string constants. And also, we will be discussing what are the different reserved words for different assemblers. We would also get to learn what are the identifiers, directives, of course, the arithmetic instructions such as the increment or decrement, addition, subtraction, multiplication, sign multiplication or integer multiplication and division or sign division. I think that's for sign. So for constant, it is a value that cannot be altered. Cannot be altered by the program during the execution. Thus, as its name implies, the value is constant. The key difference between a variable and a constant is that a variable may change its value during the program execution, while a constant, as a general rule, it cannot be changed. Also, a variable can be defined either globally or inside of your subprograms, while a constant, it should be declared, I think, it should be declared globally. So, to give you an example of a constant value, if you are writing a program which consists of more than 1,000 of codes, and for some instance you need to perform a computation over and over again, so it would be very useful if you will be defining a constant as part of your program, because as a good practice in development, a duplicate code is uh, is not good for the eyes. Well, that's just only an opinion, but it's a good practice to have a constant declared. Okay, let's proceed for integer constants. An integer constant or integer literal is made up of an optional leading sign, one or more mm, digits, and an optional suffix character called a radix, indicating the number's base. So the following are the radix. It should be capital uppercase H or lowercase h for hexadecimal, uppercase Q or lowercase o for octal, D for T for decimal, and B and Y for binary, and R for encoded real. So if for assembly language, if no radix is given, by default, constant is assumed to be decimal. Below are the examples: 26 decimal, 26D, 1101011B, it is binary, 42Q for its octal, 42O is the same for octal, 18H for hexadecimal, and 0A3HX is for hexadecimal as well. Just just take note, a hexadecimal constant beginning with a letter must have a leading zero to prevent the assembler from interpreting it as an identifier. So for integer expression, an integer expression is a mathematical expression involving integers, value, and arithmetic operators. The below table is the operator and the precedence level of the arithmetic operators. So anything that's inside a parenthesis, it should be evaluated first, followed by the unary plus or minus. and then the multiply, divide modulus, and lastly is the add or subtract. I think this is where you are all familiar with this with the PEMDAS rule. It's almost the same. I think it's the same, yeah, for the PEMDAS rule. So for character constant, a character constant is a single character enclosed in a single or double quotes. Masum stores the value in memory as the character's binary ASCII code. So examples are for constant character A enclosed in single quotes, it is stored in memory with the corresponding binary ASCII code. And another example is a user can define a constant value of M for male and F for female to identify the gender of an individual. For string constant, it is a constant in a sequence of characters, including spaces enclosed in single or double quotes. Below are the followings. First is the University Luzon enclosed in single quote, followed by UP using double quotation, ABC using single quotation, and the integers 1, 2, 3, 5, 6, 7. Even the value is integers and it is enclosed by a quotation, the program will treat it as a string constant. So just let me just show you something. So if you will be defining a string constant that has a apostrophe inside the string, like this, like that, you will be encountering error if you will have if you will use a single quote, and it will be very difficult to place a single quote from one string to another. So it is advisable to use a double quote like this and have this apostrophe inside along it. So you will not be having a difficult time, and you will not receive any errors when you are compiling. So reserved words have a special meaning to the assembler and cannot be used for anything other than the specified purpose. They include instruction mnemonics, move. I believe we have already used that in the previous discussion. Add, mule for multiply, jump, and call. We also have for directives such as the data, that code, and the operators in constant expressions like 5, 5 plus 5, 10, 10 times 10. Predefined symbols such as at data we should constant values at assembly time. And also, reserved words cannot be used as an identifiers. And these reserved words may vary from one assembler to another. So so far we have identified 3 assemblers: the NASM, the network assembler, the MASM, the Microsoft, and the TASM. So these reserved words is a general rule. You cannot use it in your program because they have their own purpose. Every time you will use a reserved word, you will receive or encounter an error. So identifiers. These are names that the user or programmer choose to represent variables, constants, procedures, or labels. So as a rule, identifiers can have 1 to 247 characters. These are not key sensitives. It can begin with a letter, underscore, or special characters, and can also contain digits after the first characters. But your identifiers cannot be reserved words. That is the general rule. So as a programmer, it is also a good practice to use a identifiers when you are declaring a variable. Uh, some people observe a naming convention in creating their own identifier. For example, if you will be using a variable, uh, you will have a, let me just show you. So as if you are going to declare a variable, normally they put it like this: v underscore and then the name of your variable. Others, if they are going to create a function, they do it like this: underscore and do the function name. Or same thing with other objects such as stored procedures. If they will be naming an object, they have this. It's not these are not mandatory, but these are a good practice in development. Something like that. And other developers also observe the camel camel case, wherein you get the small letter, then followed by uppercase, then lowercase, and then uppercase, something like that. So those would fall um, in identifier. So it's up to the programmer or developer what name he will use to represent the variables or constant he or she is defining. But of course, we have these rules, and we have also the general rule as for the servers. Just a second. Sorry for the background noise. May mga bata. Okay, so let's proceed with directives. So directive is a command embedded in the source code that is recognized and acted upon by the assembler. It can define variables, macros, and procedures. In MASM, directives are case insensitive. For example, it recognizes that data and that uppercase data and that uppercase D data as equivalent. It's the same, but in NASM, it is case sensitive. So below is the example. You will use a identifier myvar, and you will use the word as a directive and assign a value of 26. And then you will move to the 32 accumulator register the value myvar. So based on the example, the myvar have a value of 26. Okay. So another directives are the EQ or the equate. The EQU directive is used for defining constants. The syntax of the EQ directive is as constant name, the EQ directive, and the expression. So below are the four examples I have listed. You will be assigning or equating the total students with a value of 50, and the length with you will assign a value of 20, and width with a value of 10. Don't be confused with the first word right before the EQ. Those are just identifiers. You could actually use any identifier name as long as you follow the rules that are mentioned earlier. So instead of, if you will compute for an area which is a length times width, and instead of changing the value from time to time, you just have to create a identifier area and put the expression right after the EQ directive. So we also have the percentage sign assign. It is used to define numeric constants, like it's the same DEQ. This directive allows redefinition. So the key difference between EQ directive and assign is that the assign can be changed, wherein the EQ will not be changed because it is a constant. Defining it will define both numeric and strings. Strength, string length, uh, like the macro assign, in that it creates or redefines a numeric value to a macro. The difference is that with strength length, the numeric value is in the length of a strength. This directive will just return the number of strings that are used in a string. For example, if you use a strength length in a character XYIEN, it will return 5. XYI. Yeah, 5. So let's proceed for substring. So substring is used to extract individual letters. In assembly language, it is used as the following: um, percentage signs, substring, my car, and then the string that you would like to perform the substring operation, and followed by the location where you would like to get the value. So in the first example, we define 1. So it will return x because x is the first value, and 2 for y, and 3 for z. But let me show another example for Oracle. We also use this in Oracle, the substring. Uh, it's like this. Like substring, university, etc. So on, and this, but this is for, I'm not sure if the same syntax follow with other programming language, but in Oracle it can be performed like this. First, you specify the location where the function or substring would start. In our case, if I wanted to return I would like to get the value of only, then I would need to count how many strings are there before the value I wanted to return. So in this case, we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 12. So 12. Then after that, if I would like to return 2 integers of only, so I could get the of word like that. So this will result into returning the value like that. So that's the same with the assembly language as substring. Is there any question with regards to this directive? No question? Okay, I will just proceed. So we are now in the arithmetic instructions. So we will be discussing the increment and decrement instructions, and as well the addition, subtraction, multiplication, and division. So to start off with increment and decrement instructions, so basically it just only add and subtract. Okay. So for increment, the logic is like this. So that's the destination and the destination plus 1. So for if you wanted to increment the base register for 16-bit, so you just use the increment instruction, the register, and then it will just be incrementing it by 1. So right after the semicolon, it's basically we're just expounding this. Uh, we are just expounding this the increment bx. It's like this. Same thing with the decrement. So example below is I have identify my word and use a word and assign a 1000 hexadecimal. So I've incremented it by 1. So the value of the identifier my word is now 1001 hexadecimal. So I wanted that value and I wanted that to move it in the base register my word and have it decremented by and have it decremented. So I will just use the same syntax. This should be, I'm sorry, this should be bx, not bc, because I have already assigned, I have moved the my word value to base registry. So this should be bx, not bc. Yeah. So why? This is it. There. So just a few notes. Increment and decrement is better than add than subtract, because the decrement takes less space, and they are both executed at the same speed, but in comparison to addition and subtraction, the increment and the decrement takes less space. But of course, there are some features that can be attained only using the addition and subtraction. So you can see based on the example below, you can only increment it by 1, but I was not able to test if I could increment it more than by 1. So I was not unable to install the emulator. So I was unable to test it. But bottom line is, if you will be comparing the increment and decrement, this is better than addition and subtraction because of the performance issues. So for the addition of subtraction, uh, it adds or subtracts operand to a destination operand of the same size. So the logic is the destination, and then the destination itself, or plus or minus the source. So addition and subtraction instruction can take place between register to register, memory to register, register to memory, register to constant, memory to constant, but it cannot take place into a memory to memory. So example is, if I wanted to move 10,000 hexadecimal to 32-bit accumulator. So the value of after moving the value to 32-bit accumulator register, I'll have the value now of the EAX is 10,000 hexadecimal. And if I wanted to add 4,000 to that, I could just simply use the instruction add, and then the register and the value you wanted to add. So after performing that, the value of the EAX is now 50,000 hexadecimal. And if you wanted to subtract, then you just use the sub instruction, the destination, and the value you wish to subtract. So after executing this, the value of the EAX is now 30,000 each. You could use, instead of assigning 10,000 each, 40,000 each, 20,000 each, you could use a identifier here as well. But of course, you need to define first the value of the identifier before this program. So for the multiplication and integer multiplication instruction, it can be used in a it can be performed in a 8-bit reg or 8-bit register, and either also memory 8 or 8-bit memory. You could also use it in 16-bit register or memory with 16-bit memory, and so on. There are two instructions for multiplying binary data. First is the mule multiply instruction handles unsigned data, and the imule is for integer multiply handles signed data. So multiplicand in both cases will be in an accumulator. Depending on the size of the multiplicand and the multiplier, the generated products is also stored depending upon, yeah, depending on the size. So yeah, as mentioned above, we have two separate instructions for multiplication. We have the mule and the imule. So this is a diagram which is mentioned here that uh, this is the diagram which is states here that depending on the source of the operand, the location of the other source and operand destination are selected. So for 8 bits, it is stored in your AL, which is the accumulator for 8-bit registry. And for the products, it is stored in AH. I think H is also a 8-bit registry. And for the lower part, it will be for AL. So for 16-bit, we will be using the DX and the AX, while for 32-bit, we will be using the EDX registry and the EAX registry. So for 8-bit example, I have prepared here. Uh, I wanted to move. I wanted to move an two hexadecimal value to AL, the multiplicand, the accumulator, 8-bit accumulator, and assign a 5H hexadecimal as a multiplier. I will be moving it into the base 8-bit locator and initiate it using the instruction mule and of course the multiplicand. Our multiplicand is our 5H, the base accumulator. So the product of this, so 2 times 5 is 10. So since we have a since we are using a radix, which is H for hexadecimal decimal, so the return value will be A. So A in hexadecimal, but if you convert it to decimal, it will be 10. So for 16-bit, I have assigned a 2000 hexadecimal value to accumulator 16-bit registry and assign a 100 hexadecimal to base 16-bit registry and perform the instruction. I have used mule and multiplied the base bx to ax. So the product would be 200,000 with the carry flag is equals to 1. So note that uh, so you could see on the upper right corner, you have a small table there for AX registry for 16-bit. There is a DX AX assignment of products. So how do we determine that on which is going to DX and which is going to AX? So the last 4 zeros, 4 bits are stored in AX registry. The last 4 bits, this one, the 1, 2, 3, 4, those bits are those integers are stored in the AX registry. And the remaining 4 digits, the 0020, are stored in the DX registry. So that is, and yeah, since the number is greater than 4 bit, carry flag is set to 1. So I believe the flags are already discussed by Sir Red, Sir Reden. I think it was discussed by you. So I will not be focusing on the flags, but basically these flags represent something that in this case, uh, the current flag is set to 1 because of the as a general rule in multiplication, uh, you need to store the integers to two different registries, which is the dx and ax. So for what is for integer multiplication, this is for signed integers. So I'll be using a same example. I'll be using a hexadecimal, and I'll be assigning it, moving it to data 8-bit registered, which is the DL, and FF is equivalent to -1 if you will convert that from hexadecimal to decimal. And then I'll be moving BE hexadecimal to AL. So AL this time is our multiplicand. Anything assigned in accumulator is the multiplicand. So that's the keynote there. And then you use the mule instruction to perform the multiplication. The product will be 66 decimal. And since that is less than 4, it will be assigned in the AX registry. Is there any question before we move to the division part? I think that would be the last part of my report for today.
Wala po, sir.
Okay. But in this part, everything is clear naman. Like, did I explain it clearly or medyo magulo? Yeah, okay. I would assume na clear naman siya. Just guys, remember, don't be confused with the radical signs here. Just at first it's very confusing because of the letters after the integers, but once you get to familiarize yourself with the radixes, you will get the hang of it naman na in performing this arithmetic instruction. Also, we have this table here as a guide. So just follow this and observe this. You will be able to understand it. So I'll be moving with the division or integer division instruction. It's almost the same with the multiplication. It performs arithmetic instruction it could be in the registry or the memory. It could be 16-bit or 32-bit or 8-bit. The division operation generates two elements, the quotient and the remainder, same as in algebra or in our mathematics. But the another thing to remember here is that in division there is an overflow happens. The overflow occurs when the divisor is too small. I'll show you an example later on for this. So, yep, as mentioned, it's almost the same with the mathematical with the mule instruction. There is a division for unsigned numbers and div for unsigned numbers and div for signed numbers. So below is you can see in your right portion of your screen a diagram, and the upper area is the simplified. I prefer the table than the diagram. So if you will be using a 16-bit dividend and 8-bit, your divisor will be an 8-bit, and the quotient will be stored in the accumulator 8-bit, and the remainder will be stored in AH. Those are 8-bit registers. So for 32-bit, we will be using the 32-bit registers, the DX, AX, and you will be using the 16-bit divisor as a source, and the quotient and remainder will be stored in AX and DX. Same thing for 64-bit. We will be using the EDX registries, EDX and EAX, and 32-bit as a divisor, and the quotient will be stored in 64-bit registry as well. So to understand it better, so this is a example I prepared. So remember guys, instead of using the hard coded values here like 80 or 2, you can just use a variables or identifiers. In programming, that's a good practice. But since this is just a quick walkthrough, I have used hard coded values. So I'll be moving 80 to the accumulator registry, AX, AX, and assign and move a value of 2 to our BL, that which is the divisor, and then just use the arithmetic instruction and just call your divisor. So for 80 divided by 2, that would be 40, and that quotient will be stored in AN based on our table here. And since we don't have a remainder, we will not be storing any value in the AH register. So for 32-bit, so just a sec, let me just go through this. I just prepared this division last night. So for 32-bit, what is the rule? For dividend, you will be using the DX and the AX registry. So there are two registries will be used here. So I will be assigning a 0 hexadecimal for the DX and assigning 0083 in the accumulator registry, and have and assign a divisor of 2 in the base registry and perform the arithmetic here. So basically it would say is 83 divided by 2. That would be 41, and the remainder is 1. So the 41 will be stored in the AX based on our diagram here, our table here, and the quotient will be stored in our remainder. So for overflow, same. Okay. So this is this is not a 32-bit. Just a sec. Let me just change. Ang galing, no? This is a 16-bit example because we have used DX and AX registry. So our overflow example will be 16-bit as well. So as a general rule, we will be assigning values to our DX and AX registry. So for DX, I will be using 0087 hexadecimal, and for the AX, we'll be using 0002 hexadecimal. So basically, if you combine those two, the value will be 0087 6002 hexadecimal divided by 10. So because 10 is our divisor. So the quotient of this arithmetic instruction is 87600. This value is too big to be stored in the AX register. So magkaka-error po kayo niyan. So how do you fix this? It's either you define a new divisor or probably use a higher bit of registry. Instead of using the 62-bit, you could use the 32-bit. Kasi dito sa quotient, he will be using the 32-bit registries. So I think that will work. So for integer, just a sec. integer division. So for integer, I'll be assigning a A1 hexadecimal value to our 8-bit accumulator. And that would, in decimal, that would be negative 95. Let's double check it. A1. Hexadecimal A1. See, that's A1 is in decimal, it's negative 95. Can you see it on the calculator, guys? Hello? Hello?
Lima sila. Ano? Sige.
Nakikita niyo po ba sa screen yung calculator?
Oh,
Yes,
nakita.
yes.
Yes, sir. Yes.
Ayun. Sorry. I just wanted to confirm. So, ayun. So, A1, our example, A1, hexadecimal, in decimal, that would be negative 95, as shown in your screen. There. And I'll be assigning a divisor, which is the C hexadecimal. Remember earlier when you are assigning a string using a hexadecimal, you need to first use a 0 value so that the assembly would recognize, will not interpret it or recognize it as a identifier. So mandatory yan, nalagyan mo ng 0, then followed by your string for hexadecimal. For hexadecimal, we only have 8, 1, 2, 3, 4, 5, 6. But of course, these six ABCs here, the strings represent value in decimals. For A, we have 10, B, we have 11, and so forth. So C in hexadecimal is 12. And then if you perform a division on that, you just simply need to IDIV and then the base registry, which is the BL. Then there. So after that, after writing these three syntax here, the quotient will be stored. The -7 quotient will be stored in the AX registry, and the remainder will be stored in the DX registry. So that's for my report. So I will be sharing some example as well. This is an example of a code we use in the office. So I just like to share to you the importance of using a identifiers and as well as the constants in programming. So basically, we have here 200 lines of codes here. So this is short, maikli lang to in compared to other programs we have. But as you can see, we are using here different kinds of identifiers. These are identifiers, but we use it as we call it variables. Okay. So every time we execute the program is executed, we won't be there are no hard coded values here, except for these are for business rules. So you can see here the RDO. It's already defined here in the global area declaration. So every time this value is called in the program, it will only have one value. In this case, if I, as a user, if I have inserted value of RDO. I wanted to get the report from revenue slip 4. This 004 will be assigned here in the RDO, and the value of RDO in the whole program will be 004. So that's an example of constant, and all throughout the program, it will not be changed. While in this part, in this variable declaration here, this will be changed time to time. Just to show you here, we have a loop here. See, so there is a every time you are inside the loop, the variable's value will change. So as I mentioned earlier in the presentation, the key difference between a variable and a constant is that a variable may change its value during the program. So while the constant will remain unchanged. So that's a general rule. So I think that's it for my report. Thank you, fellow graduates, for listening.
Okay. So, may mga medyo may ngayon ang dito sa amin. Congratulations, Ryan. Siguro, dali. Try kong, tingnan ko ako mag-share muna ng screen. I will try to view the code given doon sa in our tutorial point. Let's try to see that one.
Yeah. So yes, I think I can explain it.
Sige, isa lang. Para at least, for example, if anybody will be doing that, at least they can also understand. Yan isang siguro doon.
Share screen.
Yung may hard-coded na yata. Kasi yung read naman, hindi gumagana yung read. Yung may hard-coded na lang.
Ito na lang, I'll try to...
Ito, yung program with hard... Yeah, ito na. Yung program with hard-coded values yan.
Ito na lang, sir, no? Okay, let's just submit that. It's loading. Okay, can I just execute this? Okay. So I'll try to make a walkthrough on this code here. So it's almost the same of what I have discussed earlier, but this is somehow a bit complex in compared to the presentation or the actual examples I had. So here we will just skip this part because this is already part of the report of our fellow grads the previous week. So here move, we will be using assigning a value of 3 to our EAX register. This is 32-bit accumulator. Okay, and from that we will be subtracting a 0 value, so it's all still the same. So and then we will be moving a
wait Zion, i-explain ko lang yung part na yan.
Yung alin po, sir?
Yan yung part yan, yung 5 and 6. Okay, so this is actually what happened here. So we move 3 to EAX, but you notice there's a single code. It is surrounded by single code. So it is actually not the number 3. It is actually the ASCII code of yung 3 na symbol. Ano yung ASCII code ng 3 na symbol? Anybody? I think it's something baka 4 something. 4-1, baka 4-3-8, mga ganun. So that's the ASCII symbol of number 3 that is moved to EAX. So it is not the binary value na 3. Like for example, 1-1 is binary na value 3. So what the program here did is to subtract the ASCII code of 0, because the ASCII code of 3 minus the ASCII code of 0 will give us the binary equivalent of 3, which is actually 1-1. So that's the purpose of subtracting here in 0. So again, the purpose is to get the binary equivalent of the number 3, because this one is actually written in ASCII code, kaya its character. Ayun. So what is now stored in EAX after these two lines is the binary value. That's the number 3, not the ASCII code of 2 digits, 7, and 8. Yun ang ginawa nung subtract EAX. Kaya, sa akin eh.
Okay, thank you, Sir Yudes. Okay. Yeah. Ay, akala ko kasi, sir, sa MASM lang yun. Applicable din pala siya sa NASM.
May later on in the next chapters, there's a shortcut for this, pero pinakita lang dito. I think so. That's why I would like to explain this also, because in this we understand that numbers or letters like this are stored not like letter A, but they're stored in their ASCII code. So actually, yun ang that is what I would like you to remember. So yung mga strings or text are actually stored in ASCII code. So just like this 3 here is stored not the number 3, but the ASCII code of the character 3, which is something around 40 something H yata. I'm not sure with the ASCII code, but you can check the ASCII code. You can search maybe Google, or you can create a program sa C language to put the ASCII code. Pero one thing for sure, letter A, yun ang memorize ko, 65 decimal, or that's 41H yata yun. Ano gano'n?
41H?
That's ASCII code. This is hexadecimal. That's ASCII code. Hindi yan.
Okay po.
Sa
Sir, bali po, anything that is passed to registry and enclosed po sa single or double quotation, hindi po yung literal na value yung pinapasa doon, but it's ASCII binary value. Okay. Except for integers po.
Pag number yun, yun na, ito, just like for example, move EDX1, that's really the number 1. That's not the ASCII code of 1.
Okay, thank you, sir. So, yun guys, as mentioned by Sir Yud, so this is not a for literal, but it has a corresponding ASCII value, and that ASCII binary value is stored in the register. Later on, I will be looking for that ASCII binary values, and I'll be sharing it in our group chat. So we can have a better picture of what is really happening behind this program here. Although while I thought it is only applicable in MASM, but turns out it also apply in NASM. So thank you, Sir Yudes. And moving forward, so we will be in the line 13, starting in the line 13. So basically in the from line 8 to 11, it's the same. We will be assigning the ASCII binary value 4 to the EBX registry and performing a subtraction. And then we will be adding the, after performing the subtraction, we will be adding the EABX to EAX naman. And then we will be adding 0 to EAX. So anything that is enclosed in a quotation, single or double, it has a corresponding ASCII binary value, and that will the ASCII binary value will be stored in the registry, not the actual value that you can see here on our screen.
Again, dun sa line 11, so, ayan. So,
Up.
reverse, di ba? So, a while ago, from ASCII code, we have to convert that into binary. That's why we subtract 0 with line 6, di ba? Same is true with
Apo.
line 9. Convert it to binary. So, when we add, we have the binary value, which is 7. But 7, we cannot print 7 binary. That's why we have to put it back into its ASCII code. That's why we add 0 here. So that 7, the result 7 will be stored in EAX as an ASCII code. So that if we print that later, sa printing niya, what will be printed is of course the ASCII code of 7. So
so basically sir, parang ano siya, no, parang you will perform operation on the same data types.
Parang ginawang binary, then after binary, binalik mo sa ASCII code kasi again, if you want to print a string, not the binary. Hindi niya kaya i-print yung binary. Yung value ng 111, for example, hindi niya value i-print yung 111. Hindi niya, ang piniprint, yung printing natin, our system, right, will only print a string. So, because of that, we have to convert our binary value to ASCII
to decimal. I see.
Yeah, that will be the ASCII code of 7 nasa EAX. Okay, sige. Actually, ito na yung parang nung nakaraan. Actually, yun ang gusto ko. The rest will be the same with what we have done last time. Print. We just print the value of yung sum, diba? So, kasi yung here, so just continue with line 13. Halos pare-pares yung susunod. We have discussed that already. Pero just continue.
Okay, thank you. So, on starting on line 13, we will be so the value of the EAX, which is now, I think, in ASCII. Oh no. Tama ba sir? ASCII na siya dito. Sa line 13.
ASCII na yan, nasa line 30.
ASCII na.
So that's already...
We will be... where's the message? Parang ano?
Yung message yun, yung the sum is, yung lalabas ang the sum is.
Ito sir, okay.
Kaya yan.
Dito siya ginamit. Okay. Akala, ganito pala siya sa assembly. Alam ko kasi sir, dapat ma-declare muna yung, may initialize muna kung ano yung value niya before performing this. So, I thought okay. So, here, in the line 14, we will be moving the MSG, which is the value of the sum is to ECX registry. And the same with the LEN, the len. So, the value of this is equated, or use the EQU directive. So if you will follow this, you will see it will call the MSG, and the MSG is equivalent to the sum. So parang pinagpasa-pasa lang na. And then we will be using a 1. I think this represents something, not integer literal na 1. May representation to, and that will be assigning the EBX. Same thing for the system, the EAX4, which is based on the comment, we have the system call number for system right. And then we will be initializing or calling the kernel. Mhm. Mm, Nasaan na yung table? Okay. So after the program here in the start section, we will be basically parang ano to parang you are just preparing the data here, declaration or initialization, and then after that it will be called here. So in some case, we will be like said earlier, the MSG have a value of the sum is, which is a string constant. So you can see here, and then the length, which is the same. It was only passed from MSG to length, and then it is called here. So that it's in the right side of your screen, it's appearing as the sum is para siyang string pa rin siya, pinagpasa-pasa lang siya. And then you will perform a sum here sa RSB1. I think this is a directive as well. So yung tama po ba explanation ko? Medyo nagulan na sa part na dito sa ASCII.
Okay, so explain ko ulit. So again, line 5, 6, we just moved 3 to EAX, and then we converted that ASCII code 3 into its binary equivalent. So what is stored now in EAX is the binary 3, that is 1, 1 binary. And on line 8 and 9, we move 4 to EBX, that is ASCII code of 4. Then we converted that into its binary equivalent 4, which is 1, 0, 0. So what is in AAX is 1, 1. What is in EBX is 1, 0, 0. Then in line 10, we added both. So it becomes 1, 1, 1 in binary. Right, that's in line 10. It becomes 1, 1, 1 in binary, stored in AAX. But again, we cannot print 1, 1, 1 binary because the system write of NASM will only write strings. That's why we have to convert that binary into a string by adding the ASCII code of 0. So if we add that, then we have now what is stored in EAX is the ASCII code of 7. Okay? Then what we did here is to move that ASCII code of 7 to the variable sum. That's line 13. Move the ASCII code of 7 to the variable sum. That is in line number 13. Line number 14 to line number 18 was already discussed by, I think, Raiden din yata. So, yung printing. That's why if we print, we move the string to ECX, we move the length to EDX, and we just call system write 4. And then you interrupt EX80 system write i-call natin. So this will write the contents of MSG. Ano naman ng MSG? The sum is. So yun, lumabas yung the sum is. Then line 20 to 24, similar to line 14 to 18. But this time around, hindi yung MSG ang kanyang piniprint, kundi yung laman ng sum, which is actually the ASCII code of 7. Okay, this will print the number 7. And of course, line 26 and 27 is our system exit. Yeah. So, yung ginawa nyo dati na hello world, parang ito yun, yung 14 to 18, di ba? Kaya lang, we're now using, especially for sum, we're using another variable. Now, you also notice that we're just using single digits here sa printing kasi medyo madugo ang pero kaya hindi na natin yun, or you can look for codes to print multiple digits. Medyo madugo yun, pero hindi na kailangan kasi what we need here is to understand what is being done. So especially yun, we need to understand na the numbers, yung ASCII code, hindi yan yung binary na 3, di ba? That's why we have to convert that to binary, then from binary, convert to ASCII, So sometimes we do these things. Yun ang gusto ko rin na you have to more or less parang i-isip mo nila. Okay? So yeah, that's how this code uh, how this code runs. Okay? Yan na, okay na yan. Basta na na-explain yung gano'n. Right.
Okay, thank you, Sir Yudes. Meron pa po ba may mga questions or clarification or addendum? May gusto po ba kayong i-share?
Sir, may gusto lang po
Yes.
sabihin. Opo. Pwede po bang sir, i-share din po yung recording po nito after po natin mag-discuss para basahin, panoodin ko sa ulit po.
Oo, nare-record ko yun. So, siguro, okay na, no? Doon, kung may tanong pa kayo kay Zion, doon na lang sa ano. Pero I'll be also giving you some sort of an exercise. Kaya baka gagawa ko ng Edmodo account natin para doon isasubmit lang. Pero basta practice lang just for practice, okay? So, siguro,
Okay po.
let's now end this session para hindi masyadong mahaba yung naka-record. Okay na?
I'll send na lang po yung mga po na yung binary conversion sa
yung
natin,
yung code.
reference.
Okay? Wala na. Medyo
Thank you po.
amoy dito kan panis na. Okay. So, again, congratulations, Zion.